how image formation differs across microscopes, from light rays in optical straight through electrons in TEM to raster scanning in SEM, each with unique path geometry, intensity rules, and how a specimen tilt boosts contrast in the final projected image. Same fabric, two microscopes. Optical on the left blurs beyond the thin plane, while SEM on the right keeps every fiber sharp, thanks to its massive depth of focus. Electron microscopes use ultra-short electron wavelengths for atomic resolution. Magnetic lenses focus the beam like light through glass. The simplest SEM, it beats optical limits, maps scatter patterns from tiny regions, and even reveals chemical makeup with techniques like EDS. Electron microscopes crush optical ones. 1,000 times better resolution, up to 2 million times higher magnification, insane depth of focus, and bonus modes like chemical mapping. Optical just can't compete. Here's the math. Electron wavelengths lambda equals h divided by m times v. At 100 kilovolts, it drops to 3.7 times 10 to the minus third nanometer, over 100,000 times shorter than visible light. That's why electron microscopes resolve atoms. All electron microscopes start with an electron gun, magnetic focusing lenses, and detectors. Add an objective lens, projector, and screen for imaging. For SEM, drop a scanning coil and detector beam below the sample. Now the beam sweeps, signals convert to brightness, and you get a sharp point-by-point image. When the electron beam hits the sample, it scatters. Backscattered electrons reveal topography. Secondary electrons show surface details. And X-rays spill the chemical secrets, all captured to build the image. Electrons heat matter and spark 11 reactions: direct beam, coherent and incoherent elastic scattering, inelastic collisions, backscattered electrons, absorption, X-rays, secondary electrons, visible light, Auger electrons, and re-emitted from the back surface. Each reveals a new layer of the sample's secrets. Absorbed electrons dump energy as heat. Bad news for delicate samples. They also rip electrons from atoms, ionizing them. This triggers Auger plus secondary electrons, plus X-ray and the visible light from metals, cathodoluminescence in action. The beam from the sample does triple duty. First, it forms images, direct, scattered X-rays, visible light. Then reveals crystal structure via scattered electrons or X-rays. And the third one, it unlocks chemistry with Auger and X-ray spectroscopy. One beam, three powerful insights.